Hey guys, welcome to lesson 6.3, Parametric Equations. So you might be asking, well, why are we doing parametric equations? We've already learned parametric equations. And you're right, you did in section 1.5, we already learned some parametric equations. Parametric equations, remember, were when instead of relating y and x just in a regular Cartesian equation, where generally x is the independent variable and y depends on x, we're going to write separate equations for x and y so that x and y both depend on t, which is the parameter. T is just another parameter that we are introducing. Generally, it can mean time in a story problem, or it can just be t, but it gives us extra information about the problem so that for any value of t, we can find where the particle is going to be located. The reason why we're doing it again is because now we have done some trig, and we also know how to use vectors. So we're going to relate vector equations with parametric equations. The two sections that you would want to look at in your notes to find examples of this would be 1.5 as well as 5.3. We did this a little bit in the 5.3 discovery worksheet. And so you might want to check that out as well. It was that worksheet that was landscape style, and we parametrized any lips in that worksheet. So we'll go ahead and get into it. The first examples that we have are just to eliminate the parameter. And remember that the parameter is t. The parameter is this extra variable that we have introduced into the problem. And so to get rid of t, for the ones on the, for example, A, which we had done in chapter 1, it just meant that we would solve for t and then substitute into the other equation. We use substitution. In the case of this particular example, we would want to solve for t in the first equation because the second equation has t squared, which would produce a plus minus square root. We don't want to have to mess with having two different equations happening there. So we're going to solve for t in the first equation and get that t equals x minus 4, all divided by 2. And then once I have that, then I can substitute that in. So I get y would equal 5 minus x minus 4 over 2 quantity squared. And then that would be just the regular xy Cartesian equation, and then the parameter will have been eliminated. We also could convert this to vertex form if we wanted to see it by taking out the 2 squared on the bottom and making this negative 1/4 times x minus 4 quantity squared plus 5, which then tells us, oh yeah, so it would have a vertex at 4, 5 with a steepness of negative 1/4, and it would look something like that. You might not be able to see that from the parametric equations. So it's nice that then you know the shape and approximately what the graph looks like, but you lose the information. Like if I said, okay, so where's the particle at t equals 3, then you wouldn't have that if you had eliminated the parameter. So that was what we had done in chapter 1. In chapter 5 on that worksheet, we did this already, and we went through it together and we said, hey, just for the heck of it, let's square both equations. So we would get x squared equals 9 cos squared t, and y squared equals 9 sine squared t. And then, just for the heck of it, let's just add them up to see what happens, because that seems exciting, right? So then we would get x squared plus y squared equals 9 times quantity cosine squared t plus sine squared t, but cosine squared t plus sine squared t equals 1. So you end up with x squared plus y squared equals 9, which just represents a circle of radius 3, 2, 3, 1, 2, 3. There you go, centered at the origin. And we had done that on the 5.3 homework worksheet. If you can go straight from looking at this problem here to the answer because you know what that's going to create, I'm fine if you want to skip the work of squaring and adding up the equations, and you can go straight to the answer there. Totally fine. So that's eliminating the parameter. The majority of this section, though, is going to be writing vector equations and then parametric equations and going back and forth between them and parametrizing a line or a line segment. So we're going to do just one example, but one pretty thorough example of this. So we're going to start by writing a vector equation for the line through point A, which is 1, 3, and then point B, which is 3, 8, which I've already drawn for you over here. It kind of looks like it goes through the origin, but it doesn't. Okay, so to write a vector equation, I could say vector xy, or you can denote that with r, just because that's your generic resultant vector. Let's use that letter. So r, which equals xy, equals, and then we need two things. Just like when we are writing an equation for a straight line, we would need the slope and some point that it goes through. Whether that's the y-intercept or whether that's just some other arbitrary point, we need a fixed location to start it, and then the direction that it's going. And that's the same thing that I need here. So I need what's called a position vector, which means the position of your fixed location, your first fixed point. In this case, we're going to use vector OA, and that's going to be our position vector. And then we also need a direction vector, which is, well, okay, so once I'm located at A, how do I get to where I'm going? How do I get to B? And so that would be vector AB, and that would be the direction vector. Unless you be too upset that I don't have vector symbols on that. I'm working on it. I'm gonna get some vector symbols on this. And then which one of these moves? The position vector or the direction vector? Well, turns out the position vector is just giving you your first location. So that one always stays the same, but then your direction vector is going to be multiplied by time, or just if it's not time, if it's not a story problem, then it's just the parameter t. And so this is the format for any vector equation. And so for this example, what we get is I'm going to pick point A, which is 1, 3. I'm going to write it as a vector instead of a fixed point location, plus, and then once I'm at 1, 3, how do I get from A to B? So to get from 1 to 3, I would be going forward 2 in the x direction, and to get from 3 to 8, I would be going up 5 in the y direction. So that's my direction vector, or vector AB. And so I would multiply that by the parameter t, and now I've written the vector equation. Not too terrible, yeah? And then the cool thing about that is now I can parameterize a line through those same 2 points by taking the vector equation and just extracting the x component and then extracting the y component to write it as the 2 separate equations. So x equals, just read off the x equation here. You have x, x, x. Both of these are obviously times t if I would distribute that. So I get x equals 1 plus 2t. And then do the same thing for y. And I would get y equals, and then read off the y components of that. And so I would get y equals 3 plus 5 times t. And that would be my parametrization of the line that would go through points A and B. If I want the entire line, that means I need all of the values of t. So t can be anything in the real number set. Notice how I could have gotten there without doing the vector equation first. We also could have just simply taken the 1, 3, and written it here, and then figured out the 2 and the 5, again, by looking at the components. So you don't have to write the vector equation first, but sometimes it's helpful. Notice the 0.38 you actually don't see in there at all in this answer, but it happens to be where I would be located if I let t equal 1, which we're going to need for later. I also could eliminate the parameter to write this as a Cartesian equation. So if I did that, I could say that t equals x minus 1 all divided by 2. And so y would equal 3 plus 5 times quantity x minus 1 divided by 2. And then I could simplify that and get that y equals 5 halves x This would be minus 5 halves and then plus 3, which is 6 halves, so plus 1 half. And that does match what my graph shows. Notice I could have also gotten this Cartesian equation simply by taking the points and writing it in point slope form. Y minus 3 equals, find the slope between the points, which ends up being 5 halves, and then x minus 1. Notice how they're related, especially the point slope form is related to the vector form of the equation. You've got your, let me switch the highlighter real fast. Notice, if I want to highlight, you've got your 5 halves here, which is the slope. Notice how that's related to the direction vector. And then you've got your fixed point with the x of 1 and the y of 3. And notice how that's related to the position vector there. So you're just representing it in a couple different ways. Okay, so we've written a vector equation, we've parametrized the line, and we eliminated the parameter. Obviously, if I check the point slope form and I check the eliminated parameter, those should be the same equation, and that's a good way that you can check to see if you did it right. However, sometimes we just want to parameterize the line segment. We don't want the full piece, we just want the little line segment. So if I take, and I say, what if I only want the line segment from 1,3 to 3,8? And I am given a domain that I want to use. So notice with the parameterization that I had, x and y, I stuck the fixed point in there, and then I said x would need to go forward 2 to get to the other point, and y would need to go up 5 to get to the other point. That if I put in t equals 0, that I would get the point 1, 3. You can think about making a txy table. That's what we did in chapter 1. That when t equals 0, that I would be at the point 1, 3. And then when t equals 1, I'd have x would equal 1 plus 2, and y would equal 3 plus 5. So the default, when we create this, is using the domain restriction t goes from 0 to 1. So if I restrict to that, that just means, okay, here's where the particle is at t equals 0, and here's where the particle is at t equals 1. And if I only look at that restriction, then I'm only looking at the line segment from A to B. What if I wanted to switch that on you and use the domain restriction from 0 to 2? Well, if it takes me 2 seconds to get from A to B, that means I must be going half as fast. So I would simply say, okay, well, let's divide the direction vector 2, 5. Instead of 2, 5 taking me 1 second to do 2, 5, now it takes me 2 seconds to do that because I'm going half as fast. So I'm going to divide each of those components by 2. And so I get y equals 1 plus t, or x equals, sorry, 1 plus t, and y equals 3 plus 5 halves, or 2.5 t. And then this would be from t goes from 0 to 2, and it would represent the same line segment, but now instead of t equals 1, this one would give me a t equals 2 by the time that I get to point B. Notice that I could represent rays. I could go twice the distance. I could go and find a line segment down there. I could do any of those things using my fixed point and then seeing what component or what scalar multiple of the direction vector I would need to go. Last but not least, what if I wanted to parameterize the line segment, but notice that I've changed the order around, that now I want to go from 3,8 to 1,3. So that means at time equals 0, I want to be at the point 3,8 because it says I'm starting at 3,8. So all of a sudden, this gets switched around a little bit, right? Because now I'm starting at the fixed point 3,8. And then how would I get from 3,8 to 1,3? Well, I'd have to subtract 2 in the x component, and I would have to subtract 5 in the y component. And so this would get us using the domain 0, 1, which is the easiest one. So you should always use that one unless it says otherwise. This actually starts me at time equals 0 at the point 3,8, and it lands me at 1,3 when t equals 1, and you can check that by plugging in. All right, last but not least, we have some story problems on vertical, horizontal, and projectile motion. The vertical motion ones we did in the quadratics chapter, where we said your y at any time t would equal, if the problem is given in feet, which they are in the math book, negative 16t squared, that's the component for gravity, and then plus your initial velocity times time plus your initial height. And that was for vertical motion, like if we shot a cannonball straight up off the ground or something like that. We can also do problems using horizontal motion. Horizontal motion doesn't have gravity in it, so I can actually make it anything I want. I can say a particle moves just along the x-axis, so that at any time t, its position is given by x equals t squared minus 4t plus 3. And then I could ask you questions about when is the particle at the origin, which would mean x equals 0, and we could solve that quadratic by factoring and getting that the particle would equal 0 at t equals 1 and t equals 3. So I could draw my little x-axis here, and here's 0, and I know that at t equals 1 and 3 it's at 0. I could say, well, where's the particle at t equals 0? And so we could substitute 0 in for the time, and I would say that would mean x would equal 0 squared minus 4 times 0 plus 3, which is 3. So 1, 2, 3. So that means it's starting at 3, and then at 1 second it's already at 0, and then it keeps going actually this way, and then at 3 seconds it's at 0 again, so t equals 1, t equals 3, sorry for the messy, and this would be t equals 0. And then we know it's a quadratic, so it's not actually going to go back the other way. And then I could ask you questions about when is the particle traveling to the left, when is the particle traveling to the right, when is the particle stopped, which would be the second that it changes direction, the particle has to be stopped. There's a lot of things that we could do with this. We're not going to go too deep into that though, so don't worry about that. Also notice I drew it moving up slightly, just because if I draw it actually going back and forth on the x-axis, then my drawing would look like this, and you wouldn't be able to see anything that's going on because it would just be on the x-axis. That's why I gave it a slight vertical rise. Notice for the vertical motion problems, we're thinking about time as the independent and the height as the dependent. For the one that I just did, I put a little bit of rise onto it, so I was actually saying that as we travel along the x-axis, I was letting time actually be on the y-axis, which is a little bit different to make the vertical axis the independent variable, I know. And then last but not least, we've got projectile motion. So projectile motion means that the x and y can be changing. An example of that would be, I hit a baseball with an initial velocity of 70 feet per second at an angle of 34 degrees. It was 3 feet off the ground when I hit it. So we need to make parametric equations and then see how far the baseball goes. For the parametric equations, the y and the x are similar, except the y does not have the freedom that x has, and that the y is restricted by gravity. So the y component has the gravity and the x does not. The velocity, instead of being entirely in the y direction, now the velocity is actually broken up. And so part of that is the x and part of that is the y. The y component of the velocity, so I'm going to call this the velocity and then use a subscript of 0 because it's the initial, and then a y because it's the initial velocity in the y direction, would be times t, and then the initial y position here. For the x, I don't have gravity, but I would have the initial velocity in the x direction, and then the initial position, which normally we would let x equal 0 because normally we get to choose, and so why would you want it to be anything but that? And so in this case, I would have x equals the x component of the velocity. If I think about this velocity vector, I've got 70 feet per second at an angle of 34 degrees. So if I break this into the component form to see what the x and the y components are, the x component of the velocity and the y component of the velocity are simply 70 times the cosine of 34 and 70 times the sine of 34, respectively. So x would equal 70 times the cosine of 34 degrees, that's the x component of the velocity, times time, and we'll let the x initial position be 0. And then y would equal negative 16t squared plus the y component of the velocity, which would be 70 times the sine of 34 degrees times t, plus the initial y value, which is 3 feet off the ground. So these would be the parametric equations to model the path. Then, if I want to find out how far the baseball goes, approximately, because we're going to be using trace, this is one of just a few times we're going to use trace on the calculator. I can type this in parametric mode, and then I can just kind of trace along the curve until I can get to 0. So I'm going to show you this. The first thing to do is go to mode, remember, and to change down to parametric mode. And then once you're in parametric mode, oops, sorry, I didn't actually switch. Once you're in parametric mode, then go to y equals to where you can have your graphs, and I'm going to clear these out. I don't know what they're in there for. They're from when we did our last baseball example, I think. So now the x value would be 70 times the cosine of 34 degrees. Make sure to end your parenthesis, and then times t. The y value would be the negative 16t squared plus 70 times the sine of 34 degrees. It's hard on a computer, give me a break. Times time, right? That's the linear coefficient. And then a plus 3, which is the initial y value. So I've got this. I also want to check before I graph this, just to go back to mode and make sure that I actually was on degrees, which I am. So I have my equations typed in. And now let's go to window to make sure that my window makes sense. The Tmin and Tmax are how long it's going to take the baseball to travel its path, so that's probably fine. A t-step of 0.1 means I want to graph where it is every 0.1 seconds, which is fine. For the x min and max, I don't need an x min of anything on the left, but I would kind of like to see the axis. So maybe negative 10 is fine. How far do we think the baseball goes? I don't know. Let's say 400. We can always change it later, and we can go by 20s. For the y min, I don't need to see anything underground, so that's fine. And then how high do we think the baseball went? I don't know, 120 feet, something. We can check. And then you use a y scale, which is just how often we're going to see the tick mark of 20. And then I'm going to hit graph and see how I did. So it turns out I way overestimated what I needed in the x and y, which is fine. I can just go back and fix it. So I'll change the x to like 170-ish. And then the y I can change to maybe 50 for the y max and go back. That gives me a much nicer picture. So I can see that here is where it started. Notice if I hit trace, I know, it's like the one and only time, that we're tracing every 0.1 seconds. And so notice it gives me the value of time as well as the value of x and y of the path of the baseball. And so if I want to know how far it goes and approximately how long it takes to get there, I can see that at 2.5 seconds, I'm only 0.85 feet off the ground, or 859 feet off the ground. And then at 2.6 seconds, I'm negative 3.387 feet, which doesn't even make any sense. So it's somewhere in between 2.5 and 2.6 seconds. And how far does it go? Just check the x. Somewhere in between 145 and 151 feet. So we could go back to our problem. The way that we would answer this, especially on a test normally, is we would draw a quick sketch and we would say that this is, we would show here's 145 feet, here's 151 feet, and so it's somewhere in between there. And we would say it's somewhere in between 2.5 and 2.6 seconds. So we can just estimate like 2.53 seconds. I just pulled the 3 out of the air. And then how far did it go? I can say approximately 147 feet. And that's all we're going to do with that. We're not going to worry about getting it any better than that. thank you for hanging in there, and you have now survived all of lesson 6.3, and you are totally ready to go do the worksheet that's on Microsoft Teams. So have fun with that, and then when you're done with that worksheet, you would drop it in the assignment bin on Teams. Good luck, have fun.